Good afternoon, everyone. Thank you for joining us today. My name is Chandler Morris, and I am on the organizing committee of the Institute at Brown. I'll go on while this is getting sorted out. I'm on the organizing committee for the Institute at Brown for Environment Society Graduate Student Seminar. Before we begin, I'd like to thank the IBES staff for their support in making today's event possible. Thank you so much from everyone. It is my pleasure to introduce our speaker today, Dr. Adam Sobel. Dr. Sobel is a professor of applied physics and mathematics and of earth and environmental sciences at Columbia University. His research focuses on the dynamics of climate and weather, particularly in the tropics. His work connects climate science and real-world impacts, tackling urgent challenges posed by climate extremes in a warming world. In recent years, Dr. Sobel has become particularly focused on quantifying risks to society from extreme weather events. As director of the Initiative on Extreme Weather and Climate at Columbia, he led efforts to make climate science more usable and actionable for policymakers and communities facing climate risks. He is also the author of Storm Surge, Hurricane Sandy, Our Changing Climate, and Extreme Weather of the Past and Future, and hosts the podcast Deep Convection, where he engages fellow scientists in thoughtful conversations on climate policy and the human experience. Dr. Sobel's contributions have been widely recognized. He received the Meisinger Award from the American Meteorological Society and the Ascent Award from the Atmospheric Sciences section of the American Geophysical Union, and the AXA Award in Climate and Extreme Weather. As we're reminded by the devastating hurricane currently impacting the Caribbean, today's discussion could not be more timely. Understanding how our evolving climate risk translates into human risk and how to turn that understanding into effective action is at the center of today's talk. Please join me in welcoming Dr. Adam Sobel.
Thanks, Chandler, and thanks so much to the committee for inviting me and everybody at IBES for having me and being here. It's been a wonderful day so far, hearing about all the exciting things going on here and being in this lovely place. So this is the title. Too many people to credit, but I'll try and name some of them as things come up. And yeah, we'll see how it goes. I have a lot of slides, but I talk fast, and maybe I'll skip some of them, but see how it goes. So this is my outline, a little personal reflection, and an agenda, like what I'm trying to do here. And as is sometimes the case, the agenda is bigger and more ambitious than the realization. But you got to start somewhere. So, and then I'll introduce what we're talking about, what I mean when I say climate risk modeling. I still feel like I need a better word for it, but this is where we are. And then I'll present a bunch of results from my group that are more or less on hurricanes and climate, but and whose dimensions range from the basic to applied, but I'm going to try to argue that they are all connected, or maybe should be better connected than they are. And then we'll conclude with some thoughts of a broader nature. All right, so the question I started asking myself, I thought of myself as a totally basic researcher for the first, 15 years of my career. And then at some point I started asking myself this question: how can physical support climate science, which is what I'm trained to do, and probably many of you too, support climate action? I did not ask myself this when I was young, but this is the midlife crisis I've been going through. And the outcome of that is I'm going to argue for what we might call climate risk science. As I say, I wish I had a better word, but this is the word we have. And what I mean is science that makes climate impacts concrete and quantitative to inform decision making. And the informing decision making is the important part, or at least to be something that could be used to inform decision making. Word risk comes in because everything has to be probabilistic, at least in some way, although often we can't be precise about the probabilities, but we're not predicting things. I'm thinking of long range and about risk. And we have to think about extreme events, meaning individual extreme weather events like Hurricane Melissa right now, and also extreme storylines of climate as a whole, meaning like what if big chunks of Antarctic, the ice sheet fall into the sea, or the thermohaline circulation stops, or something like that. I'm not going to talk about those things here, but that's part of what we have to think about. And mostly what I'm talking about here is relevant to adaptation, meaning dealing with the consequences of climate change, as opposed to mitigation, which is reducing carbon emissions. And I'll give it why I'm talking about that. But it's also somewhat relevant to mitigation through something called the social cost of carbon or other ways, but mostly I'm talking about adaptation here. And this is why, I mean, the conclusion I've come to, and I don't think I'm alone in this, is that climate mitigation is not a science problem anymore. I mean, it may be a science problem to do it, but not to know that we need to do it. I mean, we know the problem well enough to know that we have to stop burning carbon, and the reasons we're not are not because of science. It's because of political and other issues. So do the kind of science that I do, there's other kinds of science that are critical to mitigation, but the kind that I do, and probably some of you too, which is about understanding the climate system, we've done that well enough to inform mitigation. On the other hand, adaptation is not in some ways mitigation is simple. You just stop burning carbon. I mean, of course, it's not that easy, but it is that simple in principle. Whereas adaptation means a million things to a million people in all over parts of the world, and some of them you need people want very specific and detailed information. Whether we can provide it or not is another question, but people want it to make all kinds of decisions. And some of that information, may be at the edge of what our science can provide. So I sort of came to the conclusion a few years ago and wrote this little paper making the case that for scientists doing climate science, if you want your work to be used in the sort of near term, then maybe adaptation is a better place to do it, because there's places where advancing the science a little bit can actually have an impact. So it's not to say that mitigation isn't important. I think in the big picture, it's more important maybe than adaptation. But we have to do both, and so this is just where I feel that the kind of science that's closest to some of us can have the biggest impact. And some applications, there's many others, but one is insurance, and I'm going to talk about that a lot because I've been working with the insurance industry for about a dozen years, and I've learned a lot from them, and that's motivated some of the work here. But we have a big problem with insurance in this country. Insurance is fundamental to the whole economy, and to the whole economy of the United States and the world, but we have a big problem as insurers are pulling out of high-risk states, and the government is sort of stepping in, but really not that well. So, there's a problem there, and it's not maybe not first and foremost an information problem, but information is definitely part of it. Then, under the previous administration in Washington, there was a push to adopt what they have in Europe, which is rules that you have to disclose climate risk if you're a publicly traded company, and then if you have to disclose it, then you have to first measure it, and that's a science problem of its own, and so that motivated this kind of work. It's now somewhat diminished in the United States for political reasons, but that's another motivation. And all kinds of adaptation, including building infrastructure. So this was a plan that was around for a while. It doesn't seem like it's happening now, but the Army Corps of Engineers wanted to build storm surge barriers in New York Harbor. And how do you decide what to know like the value of that? A project like that, you have to know what the risk is that it's reducing. And so there's science problems there. And all of that is the kind of science I'm talking about today. Okay, so what is it? What kind of science are we talking about? I think of it as, this is already too superficial a description, but at least some of it is a layer between what we might call basic climate science, what I was trained to do, and the user. So if you think of basic climate science as being the coupled model intercomparison project models, the big coupled climate models that go into the IPCC, those do climate projections, what the climate will look like if you increase carbon or you don't or whatever. But to make that usable for adaptation decisions, they need more. They need downscaling because they don't do extreme events well enough, and the scales of information that people want for adaptation aren't there. So downscaling, there's a lot of different ways of doing that, statistical, dynamical, but that's one thing. Bias correction. Our climate models, I think, in some ways are amazingly good, actually, but depends what question you ask. And for some adaptation questions, they're not that good. They have systematic biases. There's ways in which they're persistently a little bit different than the observed climate. And although those differences in the big picture are small, and again, for mitigation, they don't matter. But for adaptation, if you're a little bit persistently off, you have to be aware of that. I mean, you can't just use it without some kind of correction. Like if we're talking about extreme event risk, if your model says that there's 5 hurricanes a year and there's really 10, then that's a problem, even if the direction of change is right or some other big features are right. So you have to do bias correction, and, including calibration to history, and then impact modeling. So why do we care about climate? Because it affects humans and ecosystems and other things. So that's a whole nother bunch of giant interdisciplinary set of fields that exists, but that's the difference between hazard and risk. We'll talk more about that. And then uncertainty quantification, or even uncertainty qualification. I'm actually not going to be that quantitative here, but I think this is so there's sort of like a whole cottage industries of people doing these things. I think uncertainty, a lot of this talk is going to be about actually sort of deep uncertainties, where I think sort of basic climate science can make a contribution here, is that I think there's some big uncertainties that we know are there that are under-recognized, by, I wish I could control this, by the people doing these things. So that's needed. I'm going to talk a lot about that. A theme that will be there, I may not say this that much in the middle of the talk, but I'll say at the beginning and the end, is that there's a lot of this kind of work that's been going on for a long time in many sort of parts of academia and government and the private sector. A lot of what I'm talking about here is not fundamentally new, although the specific work I'll show will be, but a lot of the basic ideas are not. But it's very sort of fragmented space where people do sort of similar things, but a little bit differently in different sectors. And a theme I'm going to try to bring out, at least at the beginning and the end, is that we could have a more systematic understanding. We could have more of like a field of how to kind of do this stuff than we do. I would say now we have sort of multiple little sort of subfields that aren't connected as well as they could be. So that's a theme. So what is it? When we talk about risk, this is language I learned from the insurance industry, but I think it generalizes somewhat. It's used by others as well. Physical risk, we can think of as having three components: exposure, hazard, exposure, and vulnerability. The hazard is the geophysical part. It's the part that's related to the climate. So let's imagine we're talking about extreme weather events, as I am. Then the hazard is, for one event, it's usually we measure it by the most extreme value taken by some physical variable during the time of the event. So if it's a Hurricane Melissa, it's what was the highest wind speed, at a point, or you could have a description of that as a spatial field. How deep is the flooding? Some metric of the geophysical thing that we're worried about. And then exposure is whatever you're worried about the risk to. I mean, if it's insurance, it would be buildings, but of course human life and well-being, ecosystems, whatever. Something that you can put a number on that you're worried about and is distributed spatially. And then vulnerability is what connects them. So it tells you for a given level of the hazard, if the wind speed is this high, how much of the building is going to be destroyed, and so on. And so that's for one event. That tells you the law. Those are like the three components of the loss, like what is the thing, what's the hazard, and how much of it, this is the fraction that's being destroyed. And then if you have that from one event, then you can take lots of events, and if you know the probabilities of those events, then you can have whatever statistic of loss you have, and that's sort of the definition of risk. And you can imagine then that if you want to reduce risk, you're going to change one or more of these things, and that's adaptation. And again, the sort of diversity, the sort of lack of coherence in this field is that in different sectors, and I'll give just a couple of examples at one point or another, the scales at which these things are so I mean, in other words, many people are doing this, doing something to estimate risk to something, but it's done at very different scales with different kinds of data, different amounts of physics versus empiricism, different resolutions, different, ways of handling uncertainty, and the consequences are sort of not fully understood. In other words, why do these people do it this way and why do those people do it that way? Maybe there's good reasons, but it's not always clear, I think. And so that's one of my themes. So now to get to a little more specific, I'm going to talk about hazard for a while because I'm trained as an atmospheric scientist and that's my expertise. So most of the talk is going to be about hazard, but there will be some exposure and vulnerability near the end, and I'm trying to keep it all connected to that, to be motivated. So here's the framing for hazard. If you want to know the probability of a big hurricane hitting Rhode Island, a category 3 hitting Rhode Island, it's just about never happened in the modern historical record. So what's the probability of that? That would be part of the hazard information. If it hasn't happened in the historical record, the naive estimate from history would be that the probability is 0. But you sort of know the probability is not 0 because some have come close and it probably could have happened and the data is not that long. So what do you do? So that's the problem with the historical record. Good thing about history is it's real. You're not relying on anybody's model. The cons are you don't have enough data to measure the rare events. And the rare events, when we're talking about extreme weather, do the majority of the damage. A few big events is much worse than a lot of small events. So that thing you don't have enough history to know is really a problem. The other problem, of course, is the climate's changing. So even if you had a lot of data, it might not be representative. The past may not represent the present, let alone the future. So that's a problem. So we have climate models. Some of us love climate models. They're physics-based, as much as we can make them. They represent climate change organically. You put in the carbon, the climate warms up, the jets move, and the weather systems happen all due to the laws of physics as best we can imagine. It's a sort of, in principle, the right way to do it. But they're not that good at lots of kinds of extreme events because of resolution and other issues. The hurricanes in typical climate model are not good, as just one example. They're expensive and hard to use, as some of you probably know from experience. And they have some systematic errors, which I think are pretty small from some perspectives and pretty big from other perspectives, and we'll talk about that. And they don't model the impacts at all. I mean, they're models of the natural system. They're not models of human impact. So then, in the insurance industry, being aware of these two problems, they invented something called catastrophe models. And catastrophe models are really interesting because they're a sort of subfield of science that was more or less invented in the private sector. It isn't that well known outside of it, but I think the rest of us sort of have a lot to learn from cat models. So I'm going to talk about them. So they have all these components: exposure, hazard, and vulnerability. This is a schematic that I got from somebody in the industry, and from that they estimate loss. They also have financial models that predict how much insurance would have to pay out in some given event or year. The hazard is based on historical data, not physics-based simulation, which means they have a historical record, how many hurricanes happened that hit the US coast in the last 100 years. And then they make some statistical algorithms for making more that look like those but are different. So schematically, you can sort of imagine if one hit this place on the coast and one hit that place on the coast, but none hit it between, well, it probably could have hit in between. So maybe you should put one there too. It's much more sophisticated than that, but that's the basic. You're sort of making more that look like the existing ones. They tend to treat the whole historical record as one thing to have enough data, because you never really have enough data. So they tend, until recently, to not really be aware of trends, and they haven't put climate change that well in. But they're not doing, at least until very recently, and still mostly, they're not using physics-based methods, which makes it hard to do climate change. Vulnerability and exposure data are probably, for buildings at least, in big insurance markets like the US, the cat models probably have the best data. They know a lot about what buildings are there. They know a lot about their how likely they are to fail in a given event. And they have data on past insurance claims to calibrate everything, but a lot of that data is proprietary. Almost all of it is proprietary, which means I can't get it, you probably can't either. And that's a problem if we want to do this work in the public space. So the work I'm going to talk about is, in our group, we've been doing now for about a decade what we might call climate condition catastrophe modeling, like building on what the insurance industry does, but keeping climate change in it. And the industry sponsored some of this work, as well as government agencies. Sometimes we call it statistical dynamical downscaling. And so to compare it to industry, I get this talk to industry people sometimes. We do everything open source and peer reviewed because we're academics and we want to share knowledge and get critiques from our peers and so on. We believe in all that. We have a little more physics to handle climate change. Not that much, actually, but more than the industry cat models have. We take a global approach. So another limitation of the industry cat models is that they are country by country, or at least region by region. So model for US hurricane, and they tend to be in the models where there's a lot of insurance, because that's where the money is. So pretty good models for US hurricane, like Madagascar, cyclone, Bangladesh, not very good. So we do it globally, because we want to, we're not doing it just for the insurance industry. We want to do it, for climate adaptation broadly, hopefully. And I'd just like to give credit to Kerry Emanuel, who got me interested in this whole thing about 20 years ago, when he invented a pioneering model that sort of inspired a lot of what we did after that. And he's been a supporter and a collaborator since then. So some results from our group. This is the model we made. I'm not going to show you the equations, but it was built by my excellent young colleague, Jiaying Li, when she was a postdoc. She's still with us, more senior person now, but was collaborating with Susanna Camargo and Mike Tippett and me. And what it does is it takes climate information, which can, on a grid, monthly data that can come from reanalysis, like an observation-based data set, if you want to do the historical climate, or you can get it from a climate model. And then using the historical data on hurricanes, we do some, basically, a form of regression to derive some rules for sort of time by 6-hour time step by 6-hour time step to decide when a hurricane should form and how it should move and whether it should get stronger or weaker and by how much. So we're not really solving the equations of motion, but we've used empirical data to build up relationships between how hurricanes evolve and the large-scale climate. And then if we want to do climate change, we put the climate, we don't change those rules, we just change the input climate data. And so we can take, so we take data from like the CMIP models and we can generate projections of climate. We don't have to believe the hurricanes that are in the climate. They do have their own, but they tend to be too weak. And this way we're more calibrated to history and we have the full spectrum of extreme storms because we built it that way. And so that's what we do. We get projections of, we generate, as the industry cat models, we generate lots and lots and lots of synthetic storms very cheaply from which we can estimate like the probabilities of rare events. I mean, whether those probabilities are right or not is always, you have to worry, but we do our best. Okay, here's the first time, so here's my first actual result. This is from the first paper we wrote 5 years ago about climate change with this model. We published a couple papers just comparing it to historical data, but this is the first climate change one. And Chai-Ying came and said to me, I can't publish this result. It's embarrassing. And I said, no, you have to publish it. What it shows is, because it's the state of the science, this is the number of tropical cyclones on the planet, so those reaching at least tropical storm intensity, 35 knot winds, each year versus time going from the past up to the future to 2100, where we're downscaling about half a dozen different climate models. This is from CMIP 5. And the observations up to some point are in the black, and the shading is the model simulations. And the fact that we agree, there's about 80, 90 per year, that's the number. And the fact that we agree with that is just because the model's calibrated to agree with that. It's no sign of success. But then going into the future, there's two branches to the solution. One goes up and one goes down. And you might think it's because we're downscaling different climate models. It's in fact not that. Those are the different colors of shading, and all of them have these two branches. What it is that it's actually, what I didn't tell you is two versions of our model. And remember, I told you put in some climate information to decide what the hurricanes will do. And one of the variables we put in is a humidity variable, how much water vapor in the atmosphere. And we use two different ways of measuring that with the same underlying information, but one is called the relative humidity. That's the ratio of how much water vapor there is in the whole column in this case, over the saturation value, the maximum you could have, which is temperature dependent. Versus the other one is the saturation deficit, which is just subtract the difference of those two numbers instead of the ratio. And if you make maps of those two fields, relative humidity and saturation deficit, in the current climate, and you choose your colors right, you cannot tell the difference. They look exactly the same, but they behave very differently under climate change because the relative humidity, all our models predict more or less, will stay constant. But that implies through simple math that the saturation deficit goes up. And hurricanes, so it depends, do you think hurricanes are sensitive to the relative humidity or the saturation deficit? There's some theory that says the saturation deficit, but it's not a well-developed or proved theory, so we really don't know. And so we have two models that do different things. Pretty big difference, right? It's not just the magnitude, it's the sign of the change. And actually, a lot of climate models, the best high-resolution climate models that do hurricanes suggest the number should go down. But there's a few good ones that suggest it should go up, not suggest that simulate that it will go up. And so we don't really know, and we wrote a little review paper saying, this is our weird little model, but it's actually, I mean, the reasons may not be the right reasons, but actually the overall state of hurricane science is such that we actually don't know the answer to this. We don't know whether the future will have more or fewer. We expect them to get more intense, but the number, and then we're pretty confident about that, but the number we don't know. And in fact, we don't know why there's 80 or 90 per year now and not 1/3 of that number or 3 times more. So that gives you an idea of why we don't know the changes. So that's my first example of what we call an epistemic uncertainty, meaning we sort of don't know. I mean, we know what we don't know, but like I can't give you a probability that this one is right versus the probability that one is right, because in history they both agree equally well. So, which is to say that climate change doesn't have an analog in the recent past. Okay, this is some work that we did with Aon, a reinsurance brokerage company that's been sponsoring some of our work. And they asked us to, what we did was they have their own CAP model that does hurricane loss, and they have their own tracks. And we simulate changes in frequency and intensity of storms hitting each section of US coastline. And then we use those changes per category, per stretch of coast, to change the frequencies of the events in their model so as to get estimates. And then they run it through their exposure and vulnerability, which is proprietary. We never get to see it, to estimate changes in hurricane loss in future periods. So we did a couple of climate scenarios. This is with CMIP 6 now, for those of you who know that, SSP 2.4.5 and SSP 3.7.0. These are two different warming scenarios. This one warms more than this one. And this is changes in hurricane loss as a %. And this is the statistics are average annual loss, 100-year event, 200-year event. These are like different return periods, okay, if that makes sense. The 1 over the return period is the probability that such an event will happen in a given year. This is how they think about risk, different metrics. And there's two branches of the solution because of the two versions of the model that I just told you about. So they pay us all this money, we do this research, we can't even tell them the sign of the change. Kind of embarrassing, but there's still information here and there's some interesting things. One is that none of these changes are in fact very big. They're like less than 10, 20, at most 20% of the historical loss. And when you consider how volatile the loss is already because of lots of things, not just geophysical, but interest rates and inflation and then legal issues. And these are pretty small changes. So that's, if you believe our model, it says that there's maybe a lot of reasons to worry about climate change, but maybe US hurricane risk isn't the worst one. But that's this is only from wind too. So if flooding is harder and we're working on that, probably the answer would be different, but anyway. Another interesting thing is these are ensembles of lots of simulations. Both of the climate models end up our downscaling. So what you're seeing here is really the forced signal. It's not natural variability. It's not internal dynamics. It's radiative forcing. And so if this one warms, so it's definitely due to the warming. So if this one warms more than this one, why are the changes of the model that goes on the high side less, a little bit less than here? It's kind of interesting. And there's a couple of answers to that. One, there's two possible answers, and I can't tell you the relative weighting, but one is the role of aerosols. So this one has more greenhouse gases, but also more aerosols, which reflect the sun a little bit and cause some cooling that counteracts the greenhouse gas warming. And it turns out that although for surface temperature, all that matters is the total top of atmosphere radiative forcing. So 1 watt per meter squared of aerosol cooling cancels 1 watt of greenhouse gas warming, and they're the same. But for hurricanes, they actually act differently. And so the fact that this one has more aerosol, we think is partly responsible for this. The other has to do with the pattern of warming, and I'm going to talk about that next. So this is about the tropical Pacific. I know a lot of you here are interested in this, so maybe we'll have some things to talk about. So here's the problem. So then we did some downscaling. So same sponsor, Aon, and they said, we want you to tell us trends in hurricane activity. So we took these CMIP 6 scenarios, we downscaled them, and here's a map of that we produced with our model called CHAZ. If I didn't say that, the track density trend. So this is track density is just to count all this number of hurricanes that pass through a point and plot that as a number. And this is how that number is changing over the 30-year period from a particular, oh gosh, I don't remember which scenario this is. It's probably 2.4.5. But it's in this global warming projection, how much is that changing over the 30 years from 2021 to 2050? So if it's red, it means there's more storms. If it's blue, it means there's fewer storms. So our model said more storms in the Pacific, fewer storms in the Atlantic. And so our insurance industry colleague looked at this and said, well, this is interesting, guys, because the last 40, 50 years have looked like the opposite of this. The Pacific's been pretty quiet, and the Atlantic has been going up like gangbusters. So why is that? Is the past different than the future? Or is your model wrong? Or what are we to make of this? And we thought about it, and we said, we had colleagues down the hall at Lamont, our lab at Columbia, that had been working on the tropical Pacific for a long time. So we started thinking about that. And this is the map of the sea surface temperature trend in these same models over the same period. And so what the models say is that the whole Pacific's getting warmer, the whole planet's getting warmer, but the warming is the greatest along the eastern and central Pacific, so-called cold tongue. And that's what this warming pattern is very, very crudely sort of like an El Nino event in which this region warms the most. A La Nina, this region is naturally cold, there's upwelling there, and it's very biologically productive, but this is the change, so it warms in the models. And that would lead us to expect a pattern like this, because in a historical El Nino event, the pattern of change in hurricanes that we expect from the statistics of past events doesn't look exactly like this, but it looks something like this. In an El Nino, there tend to be fewer Atlantic storms and very roughly more Pacific storms. The pattern's a little different than this typically, but something like that. So we said, well, this pattern of change is sort of consistent based on past experiences of El Ninos with this pattern of change in the hurricanes. But the problem is that we think it may be wrong. So over the last 40 years, or almost 81 to 2020, you can pick different time periods and it shifts the answer a little bit, but not qualitatively. This is the trend of sea surface temperature that's actually been observed in one particular data set, the so-called HADIS data set. So it's not only been not warming the most here, but it's actually been cooling over that period. So the opposite, right, of that. And so maybe not surprisingly, if you take the observations of hurricanes, this is the track density trend, and the Atlantic has been indeed increasing, the Pacific has been decreasing. These are not exactly the opposite of each other. Oops. But pretty close. So since Amy Clement's thesis at Lamont in about the 90s, our colleagues at Lamont have been saying that the models are really wrong about this. They are wrong as a prediction of the past, but the argument has been, well, that's internal variability. The forced trend, which is what this is, because it's an average of a lot of ensemble runs. The forced trend is not worth seeing yet. The Pacific's too noisy. It's like, we don't have enough data. But now we have 20 more years of data. And if you think that it's internal variability and the models are really right about the forced signal, then if we take apart the multi-model ensemble and look at all the individual runs, and we think the models do the variability right, which we could argue, but let's postulate that for the sake of argument, then you would say at least some of the ensembles should look like the observations, even if the average doesn't, because we only live through one realization, so taking an average of a lot of runs is not the right thing. So this is an attempt to do that, and this is all based originally on Richard Seeger and colleagues' work. Got us started thinking about this, the paper they wrote in 2019, although they've been working on it much longer than that. And this is what this is. This is from the historical. So this was the past. This was the future. This was the past. So maybe that's not a fair comparison. But this is comparing apples to apples. So this is taking the sea surface temperature pattern in the Pacific and the trend and mapping it onto two numbers. So the east-west index is the east-west, the East Pacific, I forget which way it is. The east minus the west, or vice versa of that along the equator. And this is a north-south gradient, which is how warm is the equator relative to off the equator. And I'm getting myself confused, but the easy way to remember it is an El Nino is down here and a La Nina is up here. And so these are 5 observation-based data sets. And the fact that and this is the one I showed you before, the fact that they don't quite agree with each other is a little disconcerting. We don't actually know, the state of the tropical Pacific in history all that well, but they're all up in this quadrant, consistent with this picture. The models are sort of scattered around 0, but lean to the left side. This is the mean. And if you go into the future, they lean more to the lower left. And so if you believe that it's internal variability and the models are ultimately right about the force signal, then at least some of this cloud of data should overlap with the blue diamonds. And it does a little bit. So you can still make the case that it could be internal variability. But it's kind of hard. I mean, it barely, right? So we start to think the models are really wrong. And so that's a problem. I mean, these are now apples to apples. This is our model downscaling CMIP. This is the observation. Like, if the insurance industry is asking us what hurricane risk is doing, and by the way, this affects not just the future. This affects our estimate of the present, even if you write a 1-year contract, because the force signal is the only thing you know a year in advance. So this affects what the force signal is. It affects your impression of risk today. It's not just a future issue, but I'm showing trends to illustrate it. I mean, these are like radically different. And in fact, this is not just hurricanes. This affects everything. I don't know if, I can't show this, but if you know anything about El Nino, about ENSO and its impacts, it has impacts all over the world in all kinds of things, flooding and drought and fires and heat waves. And so all of those things, even though the big picture of global warming, our models might be right, but if we want to actually do risk for real users in particular places, the whole patterns can flip blue to red. Like that's a problem for climate adaptation if we don't know that. So we wrote a little paper saying that, and we've been working on it. And this is some questions. Why? What's wrong in the models? And this is one particular hypothesis that has been around again for like 30 years from Amy Clement's thesis, and we had that as our starting point, and I'll explain it a little bit, but not too much. One physical hypothesis, but more generally, even if whether we know why or not, how do we do risk assessment if the whole model ensemble is biased? Like, here's some climate variable, here's time, right? And here's our models going forward. It doesn't matter what the variable is or what models you're using. You have some ensemble, and typically what we do is we estimate, probabilities by saying how many models do what. And so here's our cloud. Well, if we know that historically reality is not in the cloud of models, what's the uncertainty quantification that handles that? It's very, very challenging. So we're sort of thinking about that problem. One way or another, it has to look something like storylines, which means make up something closer to this and try to make it at least internally physically consistent, and then think through the consequences of that, just to give people something to grab onto that may spell out what's missing from the ensemble. But okay, so now a couple more results. I have no idea how much time I'm taking, but okay, all right, great. I have to talk fast, but I'm already doing that. So here's some work by a great postdoc, Jingyi Zhuo. She's now gone to Princeton. We did flux adjustment. So we had one thesis that came from Seeger and company that was, well, the models are wrong because the mean state is wrong. There's something called the cold tongue ITCZ bias, where the equatorial Pacific along the equator is too cold in the models, and that causes the so-called intertropical convergence zone of the heavy rain belts to be too much in the south and not enough in the north. And that's a thing that every climate model has gotten wrong since the beginning of time, since the beginning of climate models. And their thesis was that because of that, it makes the trends wrong in the opposite way. There were some physical arguments there. And so we thought, okay, if that's true, then maybe we have a way to make an alternative storyline, which is to force the biases to not be there. I mean, if we could fix the ITCZ bias, we would have done it already. But there's a brute force way called flux adjustment, which used to be done a lot in the days before a couple of climate models were good enough to run without it. But it's where you, if your sea surface temperature pattern differs from observations, you just put in an artificial forcing to make it closer to observations, and then hold that artificial forcing the same and see how the future trends change, which you don't specifically intervene in. You only intervene in a constant way. So here's the observed sea surface temperature pattern. We did this with one particular model, CESM2, the NCAR climate model. This is the difference between the model and observations historically. So this is the cold tongue bias right here. It's too cold. And there's some other errors too, but this is the one we're worried about. Then after flux adjustment, which we did a standard way that, Gabe Vecchi's version, he was a collaborator on this, but doesn't really matter. You try to by force get rid of this bias, and this is the remaining bias. You don't get rid of all of it, but you can see this cold tongue bias is much reduced. And then you do future simulations. And so this is the trend in sea surface temperature simulated by the CESM2. This is what we get with the flux adjusted model. So the claim is this looks El Nino-like, this looks a little bit less so, and this is the difference between them. So this is much like things that Professor Jung-Eun Lee was showing me today that she gets from a different way that I could be consistent with this by changing the mountains. This is a little more artificial than that, but it doesn't bring it all the way to look like the observations, but it goes in that direction. So the hypothesis, maybe it's partly true that the problem is the mean state bias. And so this is one way of generating an alternate storyline. And so we're downscaling this to see how much difference it makes in the hurricanes, and trying lots of other things, and thinking about how much of it might be aerosols, might be doing what versus greenhouse gases. But it's just to say this is a physics-based way of doing an alternate storyline. Here's another way. This was another postdoc, Jonathan Lin, who's now at Cornell as a faculty member. And he had his own risk model, so another tropical cyclone model based on Emmanuel's, different than ours. He built it and finished it built it as a PhD student, finished it as a postdoc with us, and then wrote this paper, which what he did was, so he's generating tons and tons of synthetic storms with climate model input, functionally the same as ours, but different way that it works. I won't talk about it. But what he did was, so here's a future, and he was interested in the Western Pacific. So here's the Western Pacific Ocean. This is the change in the intensity of the 100-year storm. So the storm that has an average 100-year return period, how many knots is it? how does that change in, oh gosh, 2050 to 2100 period compared to pre-industrial. So, and what you see is around the Asian coast, not much change. Okay? The storms, they're getting stronger over here, but not here. But then he breaks it down, and I won't go into the details of how he does this, but he can break it down pretty cleanly into a part that's due to the global warming without considering the pattern of change in the Pacific. Basically, he takes out the years when there was a lot of ENSO one way or the other. And then you get this big increase in intensity because the warming tends to make storms stronger in his model, as in reality. But this is the part due to the pattern. Because the warming in the models is El Nino-like, that El Nino events tend to shift events eastward in the Pacific, so they don't hit the Asian coast as much. So the risk goes down in the Philippines and Hong Kong and Japan and so on. And the net change is a combination of these two. And interestingly, the sort of mean global warming and the pattern effect cancel. But of course, the models could be wrong about this, is what I'm telling you. And so then he did this other thing where he said, being able to decompose the risk into these two components, he can say, well, what if instead of doing this, this pattern goes the way that observations suggest, and it keeps going that way? What if it gets more La Nina-like? Then, so this is if the observed trend stops, and we end where we are in the SST pattern stays what it is now to 40 years in the future. You get a little bit of, this metric is the change in frequency of the 100-year storm, and the 100-year storm in the past. So if it's red, it means what was the 100-year storm is now happening more than every 100 years. And blue is the opposite. So with no future trend, you still get an increase in risk due to global warming. But if the La Nina trend pattern increases, then instead of this, you get this, which is more risk. In some cases, doubling the frequency. So this is like where the previous one was like a physical way of generating a storyline. This is like a statistical way of doing it, or a semi-statistical way of doing it. So we're just playing with different things to come up with sort of alternatives. All right. Last little bit of results I want to talk about, a little bit about exposure and vulnerability. Because these were totally new to us. And we started working with some people at the World Bank, and an economist, Brian Walsh, helped us. And then we had a great postdoc, Jane Baldwin, now at University of California, Irvine. We did our first study where we had actual economic losses, as opposed to just meteorology. So let's talk about vulnerability. So vulnerability curve, vulnerability, just to make a nod to like the social scientists, there's a whole field of climate vulnerability that's very rich and has lots of dimensions to it. In insurance, it's just a curve, okay, which is like you have some variable like wind speed, and then how much of your building is destroyed as a fraction of its value. So from 0 to 1, and these curves always have to rise monotonically because a higher hazard is always worse than if you destroy this much at 100 knots, you're going to destroy more at 150 knots. And I took out the slide, but if you really want to calculate vulnerability curves, and you look at, for example, we're talking about wind, there's wind engineers who can tell you how to calculate it for a specific building by doing simulations of the pressure field, in a wind simulated or real wind tunnel, and knowing about how the roof's nailed on. And there's huge amount of detail you can do this. We couldn't do any of that because we want to do it for a whole country at the time. This was a study of the Philippines. We don't know what all the buildings are. We couldn't do all those calculations anyway. And that's, I think, typical of this kind of work. I mean, how the engineers will tell you to do it. Most of the time you can't do it, but insurance, sometimes they do. This was a curve that Kerry Emanuel made up. No, it kind of has to have this shape. I mean, at low enough wind speed, nothing happens to your building, it's fine. At high enough wind speed, Hurricane Melissa is going to destroy like everything. And in between, it has to go up. So he made up a shape that does that, and this is a shape, and it has two free parameters. One, V thresh is like where does it start rising, and then V half is at what wind speed does it hit half, but that's really like, it's really how steeply does it rise after that point. So it's basically two parameters. It's like an S-shaped thing, but it's like where does it start rising and then how fast does it rise. So we use those as tuning parameters in the next slide I'm going to show you. So this is work by Jane Baldwin, and so in this case, we did it with observed hurricane tracks, but we're doing it now. We have a student now doing it with our model tracks to go and do future risk. But you have some storm tracks. They tell you a maximum wind speed for each storm. Then you use what's called a parametric wind model to model like how that wind field is distributed in space. For that, you get a swath that tells you what's the strongest wind speed that each point experienced. Then you have a vulnerability curve, and we did two, and basically we tuned the vulnerability curves to get the economic loss right. I'll say more about that in a minute. Here's a map of exposure. So this is, let's see, did I put the, oh yeah. This was done with the World Bank. So this is a map of, we don't have individual buildings. This is a 1 kilometer by 1 kilometer data set of like exposed asset value made by a Swiss group, David Bresch's group in ETH, based on nightlight seen from space. So it's like, what can you do when you don't have data? You know, they're clever and they figured out how to do that. Now there's new satellite data sets, but what you can mainly see is most of the assets are up here around Manila. The rest of it is, you know, much less. But then you put these three together and you can get, you know, estimate loss for each individual event. And then we try to calibrate, you know, what should our vulnerability be? How should we pick these two parameters to get the closest losses to what's observed? And the observations come from a data set called EMDAT, which has its own problems, but it's the best we can get publicly. And there's Jane, who did the work. And so here's the main result. This is metrics of skill. So we have all these simulated storms, but they're real storms. And we calculate the losses, tune the parameters best we can, and how close do we get to the observed losses. And there's lots of different statistics to compare those. This is one called the total damage ratio, which emphasizes the big events that do the most losses. There's other ways of doing it. And this is a measure of agreement where red means we're estimating too much loss, and blue means we're estimating not enough. And in the sort of and so first we just took one vulnerability curve for the whole Philippines. Because the idea is you don't want to fit too many parameters. You want to be parsimonious because you don't have data and you don't want to overfit things. So with one vulnerability curve, if we sort of fit the whole data set, we persistently get too much loss up here in Luzon, which is where Manila is. But by using two vulnerability curves, you do a lot better. And that's because, and the World Bank had household surveys that say it's justified to do that because basically the buildings are sturdier in Manila. It's the wealthiest place. The roofs are nailed on harder, or the buildings are concrete and steel or whatever. And so you can do better. No big like scientific breakthrough here. It's just, I just show it because first of all, we're proud that we wrote one paper about economic loss. Like that was a big step for us. But also, it just shows the kind of things you do when you don't have all the data you want and you can't do anything rigorously and you're sort of putting together the pieces. I think a lot of like adaptation climate science is like that. So it's just giving you a flavor. Okay, one last thing before I get to the last few slides that are, you know, sort of trying to close things out. Because I want to emphasize like how differently people do these things, this is a slide from an old sort of so-called integrated assessment model called DICE by William Nordhaus, who won a Nobel Prize, more or less for this and related things. So these integrated assessment models are, in fact, I would argue, climate risk models. They were designed to estimate the overall economic cost of climate change to inform mitigation policy, I think. And now there's much more sophisticated integrated assessment models, but these old ones are still in some amount of use. And there is a hazard and exposure and vulnerability, but this is the equation for the damage. But here, the damage is like the loss to the whole economy. The hazard is one number per time, so the global mean surface temperature, which is like a proxy for all of climate change. And the exposure is the whole world economy. And the vulnerability is a simple quadratic function that was, you know, also calibrated but made up. So like I just show this. I mean, this is maybe a little outdated, but not completely. To say that, just think about what I just showed you, where I'm focusing on like, you know, I'm talking about all the limitations of what we did with our hurricanes, but still it's like storm by storm or calculating losses and adding up. This is like, well, let's just take the whole global economy and regress losses on global mean surface temperature, but it's still a climate risk model. So it's just to give you an idea of the diversity of scales and approaches of things that are done by people in different spaces, and to say that there isn't like any systematic, you know, field that tries to like compare these things and integrate and think about when you should do what and why. So that's I have a couple slides after this, but this is a state. I didn't spend a lot of time on all these things, but I still want to say them. So the hazard can be anything from, if I think about this field as a whole, of people doing things that broadly fall under this umbrella, the hazard can be anything from global mean surface temperature to one storm or all the storms or all the kinds of different weather. I mean, think about now add the heat waves and the fires and the floods and so on. The space and time resolution could be totally different. The time frame, are you doing future, present, or past? The type of decision, you know, are you thinking about the 1 year risk or the future risk? affects how much global warming matters versus how much you need models versus how much you might trust the observations alone, despite their lack of full representation of climate change. How much do you do empirically versus with physical models? Exposure, you can know about the individual buildings, or you can have night lights, or you can just say what's the whole global economy. Very diverse. Vulnerability, sometimes you really know it, a lot of times you don't, but you have to do something. I spent a lot of my time, I think this is an area where we're interested in because it's where we feel we can make a contribution, but I think, in the insurance industry, they only recently started to put climate change in their models, and they're downscaling CMIP, and that was like the big step forward. But now we're telling them the CMIP models can be systematically wrong, like even the sign of change across entire parts of the world could be backwards. Like that's really important, but we can't put probabilities on them. I mean, the models might be wrong, but like what's the probability that they're wrong, and what would the answer be if they're, we have to think about these. Just to make one editorial comment, a thing that I've learned from doing this kind of work with stakeholders is that if they ask you a question and you can't answer it, if you're just doing research, you find another question you can answer and you write a paper, everybody's happy. But if they really need the answer to that and you can't answer it, you're kind of unethical now if you don't tell them, like, I can't answer it and this is why. So it's made me do a lot more work that has a negative bottom line and to not feel ashamed about that. That's just I'm still doing some of that right now, and I'm just justifying it. A lot of stuff is proprietary. I spend a lot of time thinking about what to do about this. A lot of the best science, or at least the most science of this type that's being done, a lot of it is in the private sector, especially in the last decade. It's boomed. In some way, the private sector is ahead of us in government and academia, and I think that's bad, both because it's not that I'm anti-private sector. I think it's great that the private sector is doing it, but it's expensive. A lot of us can't get it. Certainly people in poor countries that need it can't get it. And also, it's just not good for like public discourse. If decisions are going to be made based on data that nobody can see, that's like bad in democracies. So that's a problem. I've argued there's not a lot of systematic comparison across application areas. So my summary, to try to be positive, I think we need a synthetic science of climate risk, and I have thoughts about how to do this, and we have a US CLIVAR working group, and but I think we have to try to sort of put this together a little more, because more and more of us are doing this kind of stuff, and yet it's still very fragmented. So I think it should have a theoretical side. Like in climate science, we've learned a lot from simple models, right? Manabe got a Nobel Prize for a single column model. I mean, that is way too simple for climate predictions, and yet it was really actually quite good, and he deserved the Nobel Prize. And like, we should have that for climate risk. Like, what do you get if you make the system simpler and simpler? What complexities do you need to get what part of the answer? We have to deal with the uncertainties that we can't put numbers on. I haven't talked much about users and ethics, except for a couple of little remarks, but I think we have to know who we're doing the work for and communicate with them. Although sometimes we have to also step back and think if we know what we're doing. So there's a balance there. And I think we should it's hard to say this now in the current political environment, but I think that more of this work should be done in academia and government, even when it's hard, because we know that better data exists and it's proprietary and we can't get it. And we have to do something that seems second best sometimes. But that's what it takes to build up, the knowledge in the public sphere. Then we have to do it. So that's my summary of that. I'll put a closing slide at the end. But I first want to say, I have come to feel that in audiences giving talks like this, that it's wrong not to talk about what's happening to us right now. It's so bad. Do you guys know who this is? Anybody? It's the famous actress Rachel Weisz. Do you know the movie? It was called Agora, I think. And it's about the burning of the Library of Alexandria, right? So she's Hypatia, the Greek. She lived in Alexandria, and she's like a mathematician and philosopher. And this is like, the barbarians who want to burn down all the existing knowledge in the Library of Alexandria. And she's like, freaking out and clutching her scrolls. I feel like that's us these days, kind of. Like the whole enterprise that we came up in is really being threatened in a way that those of us in the United States couldn't imagine when we were younger, if we've been around a while. And it's really awful for the young people who've worked hard and want to have careers in this space. That we since World War II, we've had a government that supported our science, even when maybe the people in power didn't always agree with everything that was coming, or didn't like all the results, but still supported the science. And that's no longer true. And that's really, really catastrophic event for us. And I don't have any answers, but I just feel like it's wrong not to mention it. And so I, as someone who's like a super duper minor public, have some internet presence, so I get queries from people, that like young people who are applying to grad school or thinking, just out of grad school and thinking about their careers, and I don't know what to do. I mean, this is unprecedented. None of us trained for this, but I can just tell you what I'm doing, trying to be somewhat vocal in some sort of balanced way, but communicating the ways that I can communicate publicly and otherwise, thinking about how to raise money for science outside the federal government. I mean, inside the federal government too, but that's extremely challenged right now. So I mean, we could talk more about what that could look like. I'm not very good at it, but I'm doing my best because I want to try to keep making some opportunities for our talented young scientists to keep doing the work they do. And taking care of those around me, I think we all have to do that. And for those of us in positions of some little bit of seniority and authority, we have to try to do that. So I don't have any answers, but we have to be there for each other. And so I'm just trying to say something for the lack of anything brilliant to say. I don't think anybody has answers, but we have to keep doing what we're doing because the need is not going away, right? We know that much. One last thing, I do have a podcast. Some of you might have heard it, and now I'm doing a little newsletter as of a couple weeks ago. And if you go and look at it, it used to be, as Chandler said, about interviewing climate scientists, but I've been doing a brief one about my weird uncle, the starving artist who died 20 years ago, and I'm not going to talk about that. But if you go and see, looking for those discussions with climate scientists, you will find this. And if you want to talk to me about why it's interesting and what it has to do with anything else, we'll have to have a beer sometime. But that's not me. It's my late uncle, Sumner Crane. Okay. So this is what I've had to say. I hope I didn't go too far over time. I hope we have a chance to chat, afterwards or right now. And thank you so much, really, for the opportunity to be here. It's a pleasure to spend the day with you. So yeah, thanks.
Thank you so much. I think we can do a couple questions, but also the reception is outside if anyone wants cookies and seltzers. But I can pass around this microphone for anyone who wants to ask questions.
I want to thank you for this. I'm not an academic, so I can basically say what I like. And I've been writing a book right now, I'm working on it, on why if we don't deal with climate change, we're not going to have an economy that works in Rhode Island. So I came specifically to hear about this kind of stuff, and I found what you offered very excellent for what I'm thinking about, and thank you.
Thank you.
Thank you. Yeah. Thanks so much for the talk. As someone who's going through a similar midlife crisis on sort of impact versus basic science, and someone who spends a lot of time also thinking about public communication, I wanted to ask you a little bit about how you think about public communication relative to the talk you gave us today. So you spent a lot of time today talking about how inadequate climate models are to really be useful for anything that you were talking about today, right? And you use those words a lot: inadequate, completely wrong, we can't even get the sign. And I know that's not what you think at the global scale, right? But I'm curious how you think about that message and the messages that you give to different audiences and your own internal integrity in making it good enough or not good enough to convince the audience that you happen to be talking about. So just any thoughts you have on that front, I'd really appreciate.
So many thoughts. Yeah, it's a great question. First of all, yes, at the global scale, I think the climate models are right. I mean, that's why I say we know enough to do mitigation. I mean, none of this is going to change that. There's no uncertainty here that changes the conclusion that we have to stop burning carbon. So that's the first thing to say. Because it's going to whether the sign of the Pacific is right or wrong, it just redistributes risk. It doesn't, The second thing is that I think all this, in the big picture, all this uncertainty only increases the motivation to act because uncertainty increases risk, right? I mean, you sometimes see from the skeptics, if we want to be generous and call them that, the notion that, well, you scientists don't know X, Y, or Z, so why should we listen to you? Well, and we are sometimes guilty of it because we talk about uncertainty, and maybe I'm even guilty of it, we sometimes mix up signal detection and risk. I got these words from Carrie Emanuel too, but signal detection is, can you disprove the null hypothesis at 95%. A lot of climate science is phrased like that. But that's not the way you handle a problem if you're really concerned about your own well-being. I mean, if you're going to walk out into the street and you can't see around the corner and you don't know if cars are coming and there's not a light, you don't think, can I disprove at 95% the hypothesis that I'm going to get hit by a car or not, right? You worry about what if you're wrong, and the more you don't know, the more worried you are. And I think so I think a proper thought process about the uncertainty is, we have to think, and sometimes, what I'm trying to say is sometimes we write a lot of proposals that say we're going to reduce the uncertainty. Sometimes I think we're kidding ourselves, like we're not going to reduce some of these uncertainties anytime soon, but they're still there and they're part of the risk. I mean, I think one does have to do some amount of calibration to audiences. I mean, I try to not say totally different things to different people because we want to have some integrity and some consistency, but different people have different amount of capacity to absorb nuance. And I assume that an audience like this, like an audience in the insurance industry, they appreciate being told stuff we don't know because they're used to thinking about uncertainty and risk. They're pretty good at it. And it's, and so they're comfortable with that. Yeah, I mean, and I don't think the climate models are completely inadequate. I think they are the best starting point for any prediction of the future. There's nothing else. I mean, you can't do it without physics. And putting the physics in the climate, I mean, we're trying to do it with AI now, but the AI models are so far great for weather and not so great for climate. Maybe that'll be solved someday, but I kind of don't think so because we don't have enough past climate data to like calibrate them in the way that we can for weather. And so, you're leaning on physics and then you're back at climate modeling. There's no way around it. So some people say, well, we'll go to higher resolution or, I mean, whatever. We can get in debates about the future of climate modeling. But so it's just one more piece of information. Like what pieces of information do we have? We have to try to put them together. If we're going to think about it as a risk problem, I think we have to confront all the uncertainties. So I just don't think there's any honest way to do climate science for adaptation and keep silent about these things. So it is a challenge. And if I were a higher profile person where more people were paying attention to what I say than actually do, maybe I would watch my mouth a little more for fear of being misquoted or something or taken out of context. But hasn't happened yet to a point that it's made me do that.
I share a very small audience, so I don't have the problem with it. I just sort of think
Yeah, no, it's a struggle because I do write things publicly and I think long and hard about these things. And if you can so I have the record of like how I've tried to do it, but I mean, I think the other thing I think is if you're worried about the sort of battle between those who think climate is a problem and those who don't, I think it's also a mistake to try to craft your message in some way that it can't be misconstrued because you can't. Like it's hopeless. The people who don't want to honestly reckon with what you're saying who don't want to hear it, you can't get those people to like listen to you if they don't want to listen to you. So you can't worry too much. I mean, I say you can't. You can, but I don't worry too much about that because I just don't think you can win. I don't think the fundamental political problem we have is because climate scientists haven't crafted their message just right. I disagree. There's people who have thought that in the past. I just don't think that's true. I think the argument is not fundamentally about just the right way to say it. So I don't know. Those are some thoughts.
I think we have time for one more question.
Sorry, I should give shorter answers, but
Hi, thank you. I'm an anthropologist, so coming from a different sort of background. And I was wondering if you could speak a little bit about how much one can downscale in the way that you're talking about downscaling. Is it like the unit of a country, a state, a nation state?
Right.
And then my second related question was about if downscaling has largely always involved an evaluation of economic loss, or if there is also things that take into account ecological, social, cultural loss, and what those studies have tended to find, and if those studies largely sort of differ from economic loss.
The second one, I can say some, let me see. Let me start with the second one. I can't give that good an answer to that. I think economic loss is the most studied. There is a whole field of people thinking about social impacts that may not be best measured in dollars, although the economists will always put everything in dollars, even just to make it, But my sense is that those sort of more social science studies are not as I don't want to say not quantitative, but are not making sort of quantitative projections in the same way. There are people trying to reconcile this. I mean, the World Bank has ways of measuring loss that, because if you measure loss in actual dollars, then you always are emphasizing loss for rich people and not for poor people. So they do what's called well-being, which is try to recalibrate so that a dollar lost to a poor person is weighted up relative to an actual dollar. And there's stuff like that, but beyond that, I think the framework in principle can be used for anything. I mean, if you have an ecosystem that you're worried about and you can somehow describe it quantitatively, and then you can say how much a given realization of whether a climate would harm it, then you can use this risk framework just fine. The question is whether the tools exist to do that, and that's getting outside my expertise. The thing about downscaling, thank you, that's a very good question because I wasn't very clear about it. I think there's different kinds of downscaling, and some make sense and some don't. So you will see things, if you look in the private sector, there's tons of startups saying, we'll tell you your climate risk at 1 meter resolution. It's nuts. I mean, it's just completely nuts. I think it's, to me, the kind of downscaling that makes sense, it's not really about, I mean, when I'm talking about downscaling, what it really means is, it doesn't mean that I'm going to tell you your hurricane risk, the difference between the hurricane risk like here and in Narragansett like accurately. What it means is that to get any hurricane at all in a physical model, you need to have high resolution. And so if you don't have high enough resolution, your hurricanes will be bad. So you need something to make better hurricanes. And then the distribution of that, you probably still should only interpret at coarse scales. Unless the place where downscaling to 1 meter really does make sense is if your house is on a hill, then you probably do know the difference in flood risk between the top of the hill and the bottom of the hill. So there's other things like that. There's orographic rainfall, and there's things that are influenced by fixed geography that you can resolve at high resolution. Other than that, I don't think you should believe anybody who tells you that they can tell you climate risk at very high resolution. It's just that sometimes you need tools that either explicitly or implicitly account for smaller scales in order to capture the extremes that are doing the damage in the first place, even though your representation of those, the risk from those extremes may still be only valid coarsely. Does that make sense? Yeah.
Thank you so much. Please join us for reception outside.